Base RAG retrieval, augmented generation, and agentic RAG represent two distinct paradigms for augmenting large language models (LLMs) with external data. Base RAG operates as a deterministic, single-pass pipeline, while agentic RAG introduces autonomous reasoning loops where the LLM acts as an agent that plans, uses tools, evaluates retrieved data, and iterates until it fulfills the user's intent. Make sure to stick around until the end to see agentic RAG's self-correction loop in action. We'll be comparing base RAG against agentic RAG using two real-world source documents. Plus, I'll provide the sample code and setup instructions so you can run this entire open-source solution locally on your own machine. We'll use this solar system study guide as our source document to see how both base RAG and agentic RAG handle the query. This is a 5-page PDF document that will load directly into our vector database. Running our base RAG script loads the solar system PDF into ChromaDB and fires off our test prompt. The AI returns a spot-on response, explaining that Venus's runaway greenhouse effect and thick CO2 atmosphere make it hotter than Mercury. Let's execute our agentic RAG pipeline next. Using the same document and test prompt, it arrives at the exact same output as base RAG. For this solar system document, both base RAG and agentic RAG deliver the exact same correct answer when asked, why is Venus hotter than Mercury despite being further from the sun? Now let's run the exact same test on our second document, the Amazon Rainforest report. To keep things fair, both our base RAG and agentic RAG pipelines will run against the exact same data source, this concise, one-page report on the Amazon Rainforest. Let's run our base RAG script and ask, what causes the small green spots in the Amazon Rainforest? As you can see, base RAG fails to find the correct answer because the phrase isn't explicitly mentioned in the source document. Let's kick things off with agentic RAG. Watch the terminal logs closely as it processes our Amazon Rainforest document. If we look closely at these execution logs, we can trace exactly how the agent spots its mistake and corrects course. Step 1. Initial pass. The system executes a standard vector search using the user's raw question. What causes the small green spots in the Amazon Rainforest? The vector store returns chunks containing the exact literal keywords green spots. Step 2. Filtering out distractor chunks. The grader agent inspects each retrieved chunk individually. It evaluates section 1 of the PDF, which discusses ecotourism green spots and lodges, and recognizes that tourist locations do not explain an ecological or biological cause. It marks both retrieved chunks as irrelevant. Step 3. Conditional decision. The router checks the list of remaining documents. Since 0 chunks survive the grading process, the control flow routes directly to transform_score query instead of attempting to generate a hallucinated answer. Step 4. Query transformation and external domain knowledge. The rewriter agent steps in to reformulate the user's search prompt. The source PDF never uses the phrase small green spots when describing plant degradation. The LLM drew upon its internal pre-trained world knowledge to bridge the gap. It generated multiple specialized queries, concluding with the optimized vector search string. Step 5. Second retrieval pass. The retriever queries ChromaDB using the new, highly technical search string. The new embedding vector aligns perfectly with section 3 of the PDF, completely bypassing the ecotourism trap. Step 6. Final grading and generation. The grader agent validates the newly retrieved section 3 chunk, marks it as relevant, and routes it to the generator agent. The generator extracts the grounded causes directly from the PDF context. The agent avoided hallucinating by using its built-in knowledge to rewrite the query, leading it directly to the facts hidden inside the original PDF. As you can see, for the exact same source and query, base RAG failed to find the answer. Agentic RAG, however, succeeded by using its reasoning capabilities to translate our search prompt and unlock the hidden information inside the PDF. Make sure to stick around until the end to see exactly when you should use base RAG versus agentic RAG. Plus, we'll go through the installation steps and do a quick walkthrough of the code so you can run it yourself. User query. The initial question or prompt entered by the user to request information. Point 1. Encode and embed query. Converts the text prompt into numerical vectors, embeddings, that represent the semantic meaning of the search term. Point 2. Vector DB retrieval. Performs a single vector search to pull the top matching document chunks from the vector store based on similarity scores. Point 3. Prompt stuffing. Augmentation combines the retrieved raw context chunks directly with the user's original query into a single unified prompt. Point 4. Generate LLM response. The language model reads the stuffed prompt and generates a final text output based solely on the retrieved content.llm response, the final synthesized answer presented back to the user. User query. The initial question or prompt submitted by the user. 1. Intent and planning agent. Analyzes the prompt to determine the user's intent, breaking complex questions into step-by-step retrieval plans or subqueries. 2. Dynamic search/API tools. Selects and executes the appropriate tool, querying vector stores, document databases, or external APIs based on a plan. 3. Relevance evaluation and reflection. Grades the retrieved context to verify whether it actually answers the prompt or contains irrelevant information. 4. Multi-hop retrieval and refinement. Triggers a self-correction loop to rewrite queries, fetch missing details, or try alternative sources if the initial results fall short. 5. Generate LLM response. Synthesizes the validated, multi-step context into a cohesive and contextually accurate final answer. LLM response. The final refined answer returned to the user after passing through all reasoning checks. Here's a side-by-side feature comparison showing how base RAG stack up against Agentic RAG. Base RAG. Pros. Highly predictable, low latency, easy to debug, cost-effective. Base RAG. Cons. Struggles with complex questions, cannot self-correct bad retrievals, limited to a single knowledge base. Agentic RAG. Pros. High accuracy on complex tasks, handles multi-source datasets, self-corrects retrieval errors, capable of active decision-making. Agentic RAG. Cons. High latency, expensive token consumption, potential for infinite tool calling loops if unstructured. Use base RAG for internal knowledge bases with static FAQs, document summarization, simple document Q&A, and low-latency chatbot systems. Use Agentic RAG for enterprise workflows requiring multi-system data aggregation, e.g., pulling user info from SQL while querying policies in VectorDB, legal or financial comparative research, and multi-step customer support automation. Let us quickly review this base RAG Python script. Step 1. Model setup and configuration. Initializes the local Ollama LLM, Gemma 4, and embedding model, nomic-embed-text, while specifying the target PDF file. Step 2. Document ingestion and chunking. Loads the Amazon Rainforest PDF and splits the text into smaller, overlapping chunks using recursive character text splitter. Vector store and retriever initialization. Generates vector embeddings for the text chunks, stores them in an in-memory ChromaDB collection, and sets up a retriever to pull the top 2 matching chunks. Context retrieval. Query execution searches the vector store for text chunks that semantically match the user's test question. Prompt augmentation and LLM generation. Stuffs the retrieved context chunks directly into a strict system prompt and invokes the local LLM to generate the final answer. This is the Agentic AI script. Let's have a quick review. System and vector database setup. Configures the local Ollama LLM, Gemma 4, an embedding model, ingests the Amazon Rainforest PDF into chunks, and stores them in ChromaDB. Graph state definition. Defines the shared dictionary schema that tracks the active question, retrieved document chunks, and generated output across all workflow nodes. Node functions. Implements individual steps to retrieve context, evaluate relevance via LLM grading, generate answers, or reformulate the search query using scientific terms. Conditional routing logic. Inspects the document list after grading to route execution either forward to response generation or back into the query transformation loop. State graph compilation and execution. Constructs the active LangGraph workflow by chaining nodes, edges, and conditional loops, then streams the solution execution for the query. You can find all the code, sample PDFs, and setup steps in the GitHub repo linked in the description. The README covers the required LLMs, dependencies, and prerequisites built on Mac, but easy to follow for Windows or Linux. Give it a run, and if you get stuck or hit any errors, let me know in the comments. If this workflow helps you out, hit that like button and subscribe. It tells me exactly what kind of tutorials you want to see next, and it keeps this channel going.